In this lecture, we will learn about the structure of bone. Bone is again a type of connective tissue. It is quite dense. It has a calcified matrix and therefore it is a hard tissue. If you want to feel the hardness of the bone, touch your forehead. Bone is also highly vascular, unlike cartilage. It forms the framework of the body, which we call the skeleton. It protects internal organs. It enables us to move, which we call locomotion. And it is also involved in calcium metabolism and hemopoiesis, that is, production of blood cells. Bones have two components: the organic component, which is formed by the cells, the fibers, and the matrix proteins. Then it also has the mineral component, which is basically the calcium salts which are deposited in the bone matrix. There are different types of bone, and by looking at their shape, their morphology, we can divide them into different parts. Flat bones, like the bones of the skull, the sternum, the pelvis, and the ribs. Then tubular bones, which we generally call long bones, like the humerus, radius, femur, and tibia. And short tubular bones, like phalanx, metacarpals, and metatarsals. Then there are also irregular bones, which form the facial skeleton and the vertebral column. Then you have what are called sesamoid bones, which develop inside the tendons, like the patella at the knee joint. This diagram shows you the different types of bones. This is a long bone, the humerus. These are short bones, the carpal bones. This is the frontal bone of the skull, which is a flat bone. This is the vertebra, which is an irregular bone, and patella, which is a sesamoid bone. Patella is there, the vertebrae are there, the frontal bone is here, the humerus is here, and the carpal bones are there. Now let us look at the histological structure of bone. The bone, just like any connective tissue, has a matrix, cells, and fibers. The matrix is also called osteoid. It is formed, as I said earlier, from organic ground substance, which is made out of proteins and minerals. Organic ground substance and minerals. The mineral component of bone matrix are the calcium salts, namely calcium hydroxyapatite. Now, what are the cells that you find in bone? Like in cartilage, you find what we call osteoblasts and osteocytes. But unlike in cartilage, you have a third type of cell, which we call osteoclasts. The fibers that you find in the bone matrix are type 1 collagen fibers. So in bone, you have the three components: the matrix, which we call the osteoid, which is mineralized. We have three types of cells: osteoblast, osteocytes, osteoclasts, and we have type 1 collagen fibers. Now let us look at the different cells. First, osteoblasts. Just like chondroblasts, they are derived from primitive cells, here from primitive osteoprogenitor cells. They are found on the surface of the bones, and they synthesize the osteoid or the matrix and control the mineralization of the matrix. Therefore, osteoblasts are called bone-forming cells. Osteoblasts, when they are actively laying down bone, which is secreting the bone matrix, laying down bone means secreting the bone matrix. These cells have large cuboidal shape. They have a lot of cytoplasm, abundant cytoplasm, large amounts of rough endoplasmic reticulum and Golgi apparatus to produce a lot of the proteins of the matrix. Then going on to osteocytes, these are inactive osteoblasts which have got trapped within the mineralized matrix. They maintain the structure of the bones and they mediate short-term calcium release and deposition of calcium according to the serum calcium levels. Here you see an H&E section of osteoblasts and osteocytes. Here is the pink matrix and the osteocytes which are trapped within the matrix. On the periphery, you get the osteoblasts, which is secreting the matrix. So the osteoblasts secrete the matrix and then get trapped in its own matrix. And between these bone areas, you get marrow, bone marrow, which is made out of blood cells, which is filled of blood cells. Now let us talk about osteoclasts. These cells are said to be derived from monocyte macrophage cell line. Because of that, they are multinucleate and phagocytic. That means they have several nuclei in their cytoplasm and they have the ability to engulf different particles and digest them. That is what we call phagocytic. They are found in depressions in the bone, which we call Howship's lacunae. Howship's lacunae. Osteoclasts have microvilli on their surface. They can secrete organic acids to dissolve the mineral component of bone, and also they have lysosomal enzymes which can digest the organic matrix of bone. So osteoclast has the ability to completely digest both components of bone. Therefore, osteoclasts are engaged in reabsorption or resorption of bone, which contributes to bone remodeling. Osteoclasts help in calcium metabolism, and parathyroid hormone stimulates the osteoclasts. When osteoclast activity increases, more calcium is released into the bloodstream. Calcitonin, on the other hand, inhibits osteoclastic activity and reduces the calcium that is released into the bloodstream. Here you see a H&E section of osteoclast. These are its multiple nuclei, that is the cytoplasm. And this is what we call the Howship's lacunae, like a small cave in the bone matrix. So that is the bone on this side. This is an electron micrograph of osteoclasts. Now let us learn a little bit about bone remodeling. Even though the skeleton appears to be quite static, it's actually a very dynamic structure. Bone is broken down, or what we call resorbed, and laid down constantly. There's a coordinated activity between osteoblasts and osteoclasts, and this keeps the bone in its dynamic state. Remodeling is prominently seen during bone growth, fracture healing, and in sports training. In a normal resting adult, you don't see much bone remodeling. But in these three instances, you can see bone remodeling more. Now let us move on to bone types. Two bone types are described: woven bone and lamellar bone. Woven bone is basically the new bone which is laid down first. It can be laid down very fast by osteoblasts. Collagen fibers which are secreted by the osteoblasts are arranged irregularly. This kind of bone is seen during bone growth in fetuses and children, and during fracture healing, right? In a bone, when it is broken, the process of healing, you can see woven bone. Otherwise, all healthy bone in adults are called lamellar bone. Here, the collagen fibers are regularly and parallelly arranged, and you have a much better structure. It is much stronger. All bones in a healthy adult will be lamellar bone. Here you have two H&E sections on either side. This is lamellar bone, where you can see the organized structure which parallelly arranged collagen, parallelly arranged osteoblasts and osteocytes. But here this is woven bone. You can see just areas of bone matrix and scattered bone cells. Now let us learn further details about lamellar bone. There are two types of lamellar bone: compact or cortical bone, cancellous or medullary or spongy bone. Compact bone and cancellous bone. There are different names given. You might have to remember all of them. Now let's talk about compact bone. The compact bone has this typical well-organized structure which we call the Havasian system. Havasian system is you get a canal or a cylindrical opening in the middle, which we call the Havasian canal. Around this Havasian canal, you see concentric layers of bone matrix and bone cells. These bone layers are called lamellae. Havasian canals have the neurovascular bundle inside them. Each Havasian canal is joined together by cross channels, which we call Walkman's channels. The neuromuscular bundles extend into these cross channels as well. Each Havasian system, where there's one canal and several concentric layers of bone, is called an osteon. Initially, osteoclastic activity creates a tunnel in a block of woven bone. This happens during development. And then this tunnel gets lined by osteoblasts. The osteoblasts start to lay down bone in concentric circles around the Havasian canal. When mineralization occurs, these osteoblasts are trapped inside lacunae and become resting osteocytes. Each lacunae are interconnected by fine canaliculi, which contain extensions of the osteocytes. Now here you see a diagram showing you the Havasian system. So this cylindrical area, this is a osteon. And you have these lamella or layers of bone with the osteocytes. And this is the mineralized matrix. Inside you have the Havasian canal and the Walkman's canal. So this is the structure of the Havasian system in compact bone. Here again, you see a section of the bone where you have circumferential lamellae that goes around the whole of the bone. And then you have osteons, and then you have medullary cavity. So this is a cross section of a long bone shaft. Then if you look closely, you will see the central canal, which is blood vessels. You see the lacunae in which you have the osteocytes. Here you see an osteocyte with its canaliculi reaching different levels and the lacunae within the lacunae. Now let's talk about the periosteum. Periosteum is condensed fibrous tissue. It is richly supplied with blood vessels and nerve fibers, and the underlying bone depends on it for nutrition because the blood vessels enter the bone through the periosteum. Blood vessels in the periosteum only go into the Hawasian canals and nourish the bone. Periosteum also contains osteoprogenitor cells which have osteogenic potential. That means they can give rise to osteoblastic cells which have the ability to lay down bone. Laying down bone means secreting the mineral and secreting the protein component of the bone matrix and the fiber component. Periosteum is extremely important in healing of fractures, where the osteoprogenitor cells in the periosteum has the ability to lay down bone and heal the fracture. The periosteum is bound firmly to the underlying bone by what are called Sharpey's fibers. Periosteum is not present in articular surfaces and sites where you get attachment of ligaments and tendons. Here you see a H&E section. This is the bone with the bone cells and matrix, and these are the fibers of the periosteum. So they are made out of collagen fibers, osteoprogenitor cells, blood vessels, and nerve fibers. Now let us look at something called the ground section. Now, if you want to look at the Hawasian system under light microscopy, what you do is you prepare something called the ground section. That is, you take a tiny piece of bone and then grind it on a stone until it becomes extremely thin. You do not have to stain this specimen. When the bone becomes very thin, you put it on a slide and you can look at it and you see this picture. Now, because of this grinding, all the cells are dead, but you can see the lacunae in which the osteocytes were. Then you can see the fine canaliculi reaching from one osteocyte to the other. You can see the Hawasian canals and the Walkman's canals connecting the Hawasian canals. This again shows you ground sections prepared by grinding a piece of bone until it's a few microns thick. There is no staining or sectioning required. So here each of these Hawasian systems or osteons with their Hawasian canals, Walkman's canals, and the lacunae and the small canaliculi. So high power view, you see the Hawasian canal, you see the tiny thin canalicula reaching from one lacunae to the next where your osteocytes were. This is the H&E section of cortical bones. In order to do H&E section, you need to decalcify the bone because you cannot use a microtome to section the bone because it's too hard. So you need to remove the mineral component, which we call decalcification. So only the organic component of proteins, fibers, and cells will remain. Then the bone will be soft enough to slice and you can stain it with H&E and look at it. But the structure that you see is not very clear. So a ground section is the best way to look at bone structure. Now let us look at another type of lamellar bone called cancellous bone. This consists of fine irregular folds of trabecular bone. These are separated by marrow spaces. The trabeculae contain lamellar bone or Hawasian systems with osteocytes. Trabeculae are covered by a thin endosteal layer containing osteoblasts. Trabeculae are arranged along the lines of stress. Cancellous bone, again, you can see this picture where there are trabeculae of bone and they look like this if you take a high power view. And in between these spaces, you have bone marrow. These are the canaliculi, osteocytes. Here again, you can see cancellous bone with the bone marrow intervening. Again, a Chani section of trabecular bone. There can be adipocytes or blood cells and this lamellar bone matrix in between. This is called spongy bone or trabecular bone because of these spaces which are filled with bone marrow. Now let us look at the structure of long bones. Structure of long bones, you have two parts, the diaphysis, which is the shaft, and the epiphysis, which are the two ends. The central medullary cavity of a long bone is filled with bone marrow. The periosteum is thick fibrous layer and it covers the external surface of the bone and is highly vascular. The endosteum is a thin layer which covers the inner aspect of the bone on the side where you get the bone marrow. Here you see a longitudinal section of the femur. This here, the head of the femur, the inner part is made out of spongy or cancellous bone. The outer rim, the head is lined by compact bone. Then whole of the bone is lined by compact bone. In the shaft, there's a thick layer of compact bone. In area where there is very thick, like the head and the tubercles, you get spongy bone to reduce the weightage of the bone. So these two areas are called the epiphysis and the shaft is called the diaphysis. Epiphysis has cancellous bone with a thin covering of compact bone. Diaphysis has a thin outer layer of compact bone with a thin inner rim of cancellous bone. The medullary cavity lies in the middle and is filled with bone marrow. Here is a thin section of the bone where you can nicely see the trabeculae. Trabeculae is like a meshwork of lamellar bone. In between, you get bone marrow. This appears like a sponge, and that is why we call it spongy bone. It is very closely arranged and packed together in compact bone. That is why it looks as if it's really thick here, and this looks like porous, like small holes are there where you will get bone marrow. So it is the same structure, but the arrangement of the lamellae and the Hausian systems are different. Here again, you can see the difference. So this is the compact bone. You can see it's compact. All the lamellae are closely, tightly packed together. And this is spongy bone, where trabecular, spongy, cancellous bone, where there are gaps. So this area is much less heavy than this area. This is tight and thick. This is light and fluffy like. Okay, so that it gives the bone doesn't become too heavy. It gives lightness to the bone. Here again, you can very clearly see the trabecular pattern here with the gaps, the small areas, the spaces which are filled with bone marrow. And on the rim, you can see very tightly packed compact bone. Lamellae are tightly packed. Now, blood supply of long bones are very important. You have different arteries which come in and supply blood to the long bones. One is the nutrient artery which supplies the bone marrow. It enters the diaphysis through the nutrient foramina. Then you get the periosteal arteries which supply the compact bone of the diaphysis. Then you have the epiphyseal and the metaphyseal arteries. Metaphysis is actually the area between the epiphysis and the diaphysis, and they supply each of these areas. All these arteries come and anastomose within the bone marrow after epiphyseal closure. and then they supply the whole of the long bone.